Dear students, today I will describe experiment number 10 of the Power System Lab 2, which is plotting IV characteristics of PV cells. Aim of the experiment is to measure the measurement of solar irradiance and determination of IV characteristics of solar cells. However, in the absence of the PV cells or an emulator, which is not available so far, we are going to plot the IV characteristics using a suitable software. I have used Scilab because already one code is available in Scilab. First, we will discuss the theoretical background. So, what is a solar cell? Solar photovoltaic is the process of directly converting sunlight into electricity using a device known as solar cell or photovoltaic cells. Solar cells are made of semiconductor materials. When a photovoltaic cell is exposed to sunlight, it produces voltage or current, and this is known as photovoltaic effect. A solar cell is essentially a PN junction diode. A typical silicon solar cell consists of a boron doped p-type semiconductor and a phosphorus doped n-type semiconductor. When these two are connected, an electric field is created at the PN junction. When sunlight strikes a solar cell, photons are absorbed, and some photons have energies greater than the energy difference between the valence and conduction bands of the solar cell semiconductor material. After absorbing such a photon, the electron in the semiconductor material jumps to the conduction band, forming an electron-hole pair. So these are known as light-generated electrons and holes. Okay. The electric field created by the PN junction gives these electrons and holes momentum and direction. The electrons appear near the PN junction, moves to the n-type side, while the holes near the junction move to the p-type side. As a result, the potential difference is created between the two sides of the junction, and if the two sides are connected by an external load, current flows from positive to negative. And this description I have taken from reference 8, which you can find at the end of the manual. Various terminology related to solar cells: short circuit current. When the voltage across the cell terminals is 0, current flows through the solar cell. The solar cell is short-circuited in this condition. The maximum current is known as the short circuit current. Then open circuit voltage. When low load is connected, the voltage across the solar cell is known as open circuit voltage. Is typically 0.5 to 0.6 volt for a single cell. A very important concept in solar power plants or photovoltaic plants is maximum power point. It is the maximum electrical power that a solar cell can produce under standard test conditions. Under such conditions, the solar intensity is 1000 watt per meter square and solar cell temperature is 25 degrees centigrade, denoted by PM. It represents the point on the VI curve or IV curve, as we say, where the product of the current and voltage is maximum. On the IV curve, the solar cell, it occurs at the bend point of the curve, that you will see. What is IV characteristics? It's a graph between output voltage versus current for different levels of the solar insolation and cell temperature, that is known as IV or VI. Generally, the I is plotted on the y-axis and V is plotted on the x-axis. Fill factor. It is defined as the ratio of P max to the product of ISC and VOC of the solar cell, mathematically P max by ISC into VOC. What is the efficiency of a solar cell? Output power divided by input power, which can also be obtained in terms of the fill factor. What is a PV module? A PV module is composed of interconnected solar cells that are encapsulated between a glass cover and weatherproof backing. PV modules are connected in series and parallel to form PV arrays, and it is generally the PV arrays that we see. Peak watt. A peak watt is the amount of power output of a PV module produces at standard temperature, standard conditions of a module operating at 25 degrees centigrade around at the radius 1000 watt per meter square. That is what you will find at the rating of the solar panel, watt power, WP. This is the typical equivalent circuit of a solar cell, which I have taken from reference 9. So as you see, we have got a diode here. The diode signifies that solar cells are essentially PN junction diodes, and this capacitance, the parallel resistor and the series resistance describe what is the difference between a normal PN junction diode when compared to a solar cell. Now, since it is a PN junction diode, we get the general Sockle equation for the ideal diodes, which are of this form, and various parameters are described here. For example, K is the Boltzmann constant. Okay. Now, in order to simulate, we need to program these equations. Okay. Now, in the equivalent circuit, the diode D signifies the fact that without irradiation, the solar cells is equal to an ordinary semiconductor diode. The capacitance C signifies that solar cells represent the variable capacitance whose magnitude depends on the present voltage. Series resistance RS consists of the resistance of the contacts and cables. Parallel resistance includes the leakage currents at the photovoltaic cell edges. These are typical characteristics, IV characteristics of a solar cell at different irradiance, as you can see here. And this is a typical power voltage characteristics. Okay, and I have obtained both this from reference 7, which is basically the book available on electrical power generation systems at AICTE eCoomb portal. Okay. Now these are shown here, the description of the curves IV and PV. Yes. So what we are going to do, we are going to analyze the following dependencies of the solar cell. Ideally, we should have done this with an experimental solar panel, but since it is not available as of now, we are going to simulate irradiance dependency, temperature dependency, series resistance dependency, shunt resistance dependency, efficiency versus irradiance plot at different cell temperatures, efficiency versus cell temperature at different irradiance, efficiency versus irradiance at different series resistances, efficiency versus the temperature at different series resistances, efficiency versus incident global radiation at different shunt resistances, efficiency versus cell temperature at different shunt resistances. Okay. Now we will move to the code. So first of all, I'll show you where we have okay. So as we have been doing in this lab, so from this GitHub profile you can obtain this, and this is the code UG lab to experiment number 10 PV. So this is the code. Now this code has been downloaded from this website. So if you see here, this is the Scilab website where some completed projects are available. So if you search here solar, you see performance analysis of solar photovoltaic systems using computational modeling. So it is created by Mr. Jaspreet Singh of Sardar Vallabhbhai National Institute of Technology, Surat, in the year 2025. The report is available if you click on this. So if I click on this, then you see the contributor name is available. So here you see there are two things. One is the report on this, how this code has been written, what are the parts of the code, what it implements, and when you put on case files and report, you can download the code. I have downloaded this code and I made some comments, added some comments there. So we will now directly go to the Scilab. Yes. So if you can see here, I have opened this code on Scilab. So if I execute it, we have to go to the command window. So you go to the console, you see, when I go to the console, then it gives me options for all the experimentation that we are going to see. For example, if you want to see irradiance dependency, I'll just put 1 and run it. Okay. So I'll show you one such graphic window. You see, and this is one such dependency. Okay, radius dependency. So you can experiment on this. You are encouraged to experiment on this. Okay, so I'll go to the console again. So if you see here, there are so many options available. There are 10 options. So you have to run all these 10 options and again go through the code and see how the variation of the characteristics of the solar cell can be studied by using this code. Thereafter, once the experimentation is over, you are supposed to write what conclusions you have drawn from the experiment and discuss the experiment and the relevance in practical applications. So this concludes our discussion. Thank you.